I'm going to talk to you a little bit about shoring up the foundations of image analysis. I'm going to start with the weakest link, which is a particularly crap program that's on TV in the UK. But fundamentally, the idea is that all the fun stuff, you know, all this stuff that people with nothing better to do, like deformable registration, motion estimation, segmentation, that kind of stuff, that's all down there. And then there's a little bit of mathematical heroics up here, and then all this down here, people are, they leave it to a bunch of other people like me and Tim to worry about signal and image analysis and physics and all that kind of crap. And the problem with that, of course, is that whenever you're dealing with a weakest link, if you've got garbage in here, then you're going to get garbage out there. So I'm more interested in the stuff at the bottom. And so there's a message of this talk, which is that there's intelligent life in the basement, and it makes a difference. That's what I want to do. So let me tell you what the talk is, and then you can decide whether you want to stay or not. So first of all, I'm going to talk about features. Oh, yuck. Right? I'm going to talk about features, and I'll show you a bunch of examples. And following my talk that I gave on Monday, every single thing I'm going to talk about started out life in an example, us banging our heads against the wall about stuff that we couldn't do, and then trying down to basics to try and understand what it was. Then I'm going to look a little bit about texture, and then a little bit about uncertainty, and then a little bit about a shape. And I thought that the sessions we had from Guido and from Xavier were just brilliant, actually. And then I'm going to add myself a little postscript at the end, just to make you all feel fuzzy and warm and good and run out and jump in the sea, and just like I'm going to do. Okay, so we're going to start out, first of all, by talking about features, and everybody worries about step, and there's the naughty step. So there's far more to images than steps. In fact, amazingly, step changes in intensity are relatively rare in medical image analysis. We're not made like that. Okay? But most feature detectors in the world are specialized for steps. And so about 24 years ago, plus or minus 3 months, I had a PhD student named Steve Smith, and we came up one afternoon with this pseudo image which tries to contain every single intensity change you might ever think about in one single image. Okay, so there are steps of varying contrasts here. There are thin lines here. There are localized blobs, bigger and smaller. There are corners, and there are corners of varying angle. So these were supposed to be a test for edge detectors and feature detectors, and most feature detectors fail miserably. Okay? And I'll explain why in a minute. So the kind of tasks we were interested in that drove what I'm looking at, here are two of them, there are several more. I doubt that you can see these, but these are HeLa cells. HeLa, for those of you who don't know biology, comes from Henrietta Lacks, who was a lady who died of a particular cancer, but they immortalized her cell line, and that's used as one of the main cell lines. It's now been about 53 years since she, to use the technical term, snuffed it. Here's an MRI image where we're interested in this liver of trying to find out the bile structures and the vasculature in order to determine the texture of the liver. And what we're trying to do is come up with this kind of thing where we automatically segment out these cells and where we pull out the bile ducts and vessels in there. And this does a reasonable job. Okay? But it begs a question, doesn't it? It begs the following question. If we're going to start looking at features, is there a mathematical definition? This is something that Xavier Pennick and I would certainly shake hands on and agree with. If you're going to look at something, you don't want to do it phenomenologically. That's daft. It's not science. So, can we have a definition of what a feature is in order to replace this phenomenological view? And to be sure, there have been a bunch of people over the years, from David Marr onwards, who've come up with various definitions, and they've all concentrated on the various forms of gradients, the power, the absolute value of the gradient of the image. In fact, there have been alternative formal definitions available for about 30 years, but most of image analysis and most of medical image analysis completely and utterly ignored them, right, and carried on with this, doing this kind of stuff, right? In a similar way, you can ask the question, does texture form part of being a feature, which, for example, those of you who know about continuous intrinsic dimensionality will realize that actually it doesn't. So is it something that's derivative of features, or is a collection of features, or what? So David Marr argued about 25 years ago, 30 years ago, that texture can be defined as first-order statistical distributions over zero crossings of the Laplacian of a Gaussian, which is an isotropic filter, whereas Bella Ulesh had argued for the primacy of texture with so-called texton receptors. And unfortunately, Bella never lived long enough to understand modern machine learning, so he never understood the real power of the idea that he was developing, but that's been the idea that's been developed ever since. So here are two things, and we asked, is there an underlying scientific definition of a feature? Well, let me start out with one of my first graduate students at MIT. I got to MIT in 1980, and I got this young Australian kid, came to work with me. He's a little older now. In those days, he was about 22. So John came up with this little edge detector, which basically blurred the image with a Gaussian. We all know that's sinful. We then estimated finite differences, the gradients, and estimated the local gradient direction. He then came up with two nonlinear steps, which actually were the only things that made this thing work, which were called non-maximum suppression and hysteresis thresholding, and then tried to combine them over scales from can't find a cause. And so here you are, that's my image, and that's the output of John's edge detector. By the way, I should tell you that I met John about 6-8 months ago, and he finds it hilarious that anybody ever took his edge detector seriously. In fact, I wouldn't give him a PhD for it. I thought it was worth a master's, but I didn't think it was worth a PhD. Right? That's absolutely true. He went off and did his PhD for something else and actually won a prize for it. Well, you can see the problems, can't you? Look here. Corners have gone. Lines give double edges, double responses. Here, the response is contrast dependent. Corners have disappeared. You know, in short, it's not very good, actually. Well, let's take a couple of examples. One from his thesis, which is this. This is a panda. You'd have to have a pretty smart model-based recognition system to figure out the panda in that. Well, I just showed you that one, so let me not flog a dead horse. Let's take a couple of others. Here's a breast MRI. That was one I was interested in. Oh, God, with the lights here, you can't see it, which is just as well because the results are terrible. Right? And here's that liver image, and again, the results are terrible. It's a bright day. Okay, so let's actually just look at this. Well, it's the most widely used edge detector for the past 20 years. Probably the last 30 years. Everybody uses it, nobody questions it, and it's crap. Okay? Well, it works well on steps, it doesn't work at all on other features. All right, on steps, its response is totally determined by contrast because it uses the intensity gradient. That's a real problem. We're going to come back to that. Okay, and it performs very poorly on texture. Surely we can do better. All right, so let's have a look at what the world has suggested. Well, the first was, I went to MIT in 1980. I went because I was invited by David Marr to go work with him. He's a lovely, lovely man. He tragically died at the age of 37 of myelocytic leukemia. Terrible, terrible loss. He's a wonderful, wonderful person. David produced this thing called a primal sketch, and what he did was he took a whole series of different things, idealized intensity changes, rather like there were in my picture, and he analyzed the responses at different spatial scales and then tried to combine them together. And he came up with this thing called a primal sketch, which was based on this predetermined zoo of features, plus what was called feature fusion. And whenever this program was run on the entire network of computers in the AI lab, they crashed. This system never worked. Okay? It was an interesting idea, but it never really worked. Well, what about anisotropic diffusion? That's better than Gaussian. However, it's still predominantly steps. It's still the energy of a gradient. It's still going to have those problems of contrast, okay? And by the way, for those of you who don't realize, anisotropic diffusion is the same as total variation. You can do that by writing down the Euler-Lagrange equation. Well, what about wavelets? Wavelets are everything, right? Well, no, they're not. No, they're not. Most people go and use Malat's decimating wavelets. That's already a stupid idea because they're actually not either. They're certainly not translational invariant. If you move them, they're not shift invariant. You're going to get different results. Well, you could use the continuous wavelet transform, and you could actually use the complex wavelet transform that Nick Kingsbury at Cambridge does. And that, I have to tell you, is a brilliant idea. This stuff that Nick has done is really, really good. Unfortunately, it works predominantly in 1D for signals, and it gives brilliant, brilliant results for signals, and it does less well when you move into 2D. There's no obvious way, apart from really quite complex interpolation, for making this thing work on 2D or 3D signals, but it's a great idea. We'll find out why. Well, if I'm standing here jumping up and down in front of you, there must be an alternative, right? And so there is. And it's called local phase. Well, it's not as though it came around yesterday. This has been around since the 1920s, which is even before I was born, right? So features and texture are characterized by their high frequencies in the Fourier transform. That's been known for years. If you go back to the Gestalt psychologists in the 1930s and the 1920s, they were talking about this, right? Okay. And indeed, in the 1960s, John Robson and Fergus Campbell in Cambridge, which is a small, rather insignificant university in the east of England, were working on what was called contrast sensitivity and its application to texture. And they were looking at, for example, individual humans' sensitivity to these gratings, which increase in frequency and decrease in contrast. And you'd find out that every single person had a characteristic curve rather like that. And that in fact, they were remarkably similar. And from that, they deduced there were a series of bandpass filters in the human retina. It was a brilliant piece of work. And what that led on to was this idea that came from Denis Gabor, 1950, based around, you can explain from Denis Gabor, which is in fact, I've shown you an example of a chirp. Shall we sing it together? Right, this is time. Ooh. Right, low frequency, high frequency. Ooh. All right? Unfortunately, if you take the Fourier transform of that signal, you get that. Not very useful. That's why you have to introduce the concept of local frequency and phase, which produces that. In order to do that, and what Denis Gabor did in developing the hologram, was he showed that you could localize the frequencies. He used a Gaussian window to localize in frequency and time, and could then come up with what he called instantaneous frequency and instantaneous phase. Great idea. Let me show you a demonstration from 1980, which is due to Al Oppenheim at MIT. Here, I've taken two images. I take the Fourier transform. The Fourier transform is complex, right? So the Fourier transform is complex. It has an amplitude. It has a phase. I take two images. Here, I get the amplitude 1, phase 1, amplitude 2, phase 2. And now what happens is, and I don't know what Al had been smoking, it was way before Colorado legalized dope. You take the amplitude from there, you take the phase from there, you multiply them together, and you take the inverse Fourier transform. And the question is very straightforward. Do you see that? Do you see that? Do you see neither? Or do you see both? Right? Very simple question. Yeah? Now, most people, when I ask them, would say, well, you'll see them both. They're all mushed together. Yeah? You don't. Let me show you an example. There's my breast MRI. There's my liver MRI. And what I'm going to do first is I'm going to take, let's say, the power, the amplitude from here, and I'm going to take the phase from there. Oh, Just saw the phase. It's a miracle. I just saw the phase. It's less than a miracle. Suppose we switch it round. Suppose I take the phase from here and I take the amplitude from there. Well, now we get the liver. The point is that the vast majority of images that we ever deal with, and certainly in medical image analysis, have essentially got the same amplitude structure. All of the information is communicated by the phase, or at least a very large amount of the information is communicated by phase, not by amplitude. Okay? By the way, if you want to try this, if you take, do it on your own computer or MATLAB, or a real programming language if you prefer, you can take, something like a Mozart sonata and, some rap music, and you do the same thing, you'll end up very much with that. You'll see that demonstration. It's very easy to do. Okay, so here's what we end up with. You bandpass the image to determine noise. You always do that to make an even filter because you expect that the noise is not particularly biased. You then apply the Hilbert transform, which has only been known for 100 years, to this even bandpass filtered version to give you an odd filter. You then take the local energy and you take the local phase, which is the odd divided by the even. If you think about it, you can think about that as sine and you can think about that as cosine as a very simple example, okay? And you can do that for almost any bandpass filter, which is the basis of looking at wavelets. Okay, let's have a look at this and let's just run by because some of you may not have seen the Hilbert transform, astonishingly. So let's have a look at what that does. What you do is, suppose that's the Fourier transform of some particular, I'm just showing in frequencies here. Then in fact what the Hilbert transform will do, the Fourier transform of the Hilbert will produce that. It negates that and leaves that positive. Okay? More precisely, the Hilbert transform is simply the convolution with 1 over t, and since the Fourier transform of 1 over t is just the Heaviside function, the signum function, you have that the Fourier transform of the Hilbert is essentially multiplied by the signum, which is what you can see here. Okay? So that's standard undergraduate mathematics. And so what we can then do is we can take the Fourier transform, let's suppose that the Fourier transform, of 1 over t is minus j times, that's because I'm an engineer, not a mathematician. If you want to read I, that's fine. J times the signum. Suppose the Fourier transform of f has got a real part and an imaginary part, then the Fourier transform of the Hilbert is essentially minus j times that, which is essentially the imaginary part minus j there, multiplied by the signum. In short, what you find is that when you've done the Hilbert transform, the real part is just the imaginary of the untransformed, and the imaginary part is just minus times the real. And we can look at that in a rather different way. Namely, if you write it down this way, you can remember that there's a rotation in the plane through a degree theta, just gives you a little 2 by 2 matrix like that, and you can end up with that just in the case of theta equals minus pi by 2. And so for such a rotation, you can say that the two filters are in quadrature, which is why we call them even and odd. So that's just a reminder of very simple, in our case, second-year mathematics at the university. So basically, you can write this thing down called the analytic signal, which is the function plus j times its Hilbert transform. And then, in essence, what you can do is you can define the local energy, you can define the local phase. There are two things you need to take away from this little discussion. The first one is that basically, if you start off with any even bandpass filter and you apply the Hilbert transform, you'll get an odd filter, and they're a quadrature pair. And the second, and so you can define amplitude, local energy, and local phase. And the second is that frequency throws away the key information. If I just tell you that, you cannot unscramble those two components. Right? You'll need this as well. So that's the basic idea. And that, in essence, has sorted out signals. Well, that's signals sorted. And now, why is it the case that the complex wavelet transform works so damn well that Nick Kingsbury has? And the answer is because, unlike real-valued wavelets, it contains a concept of phase, just like the Fourier transform. It's exactly why, and it's exactly why he gets the great results he does. Well, that's signal sorted. Why don't we look at some images? Fortunately, there were two women. They never got the recognition they deserve, I suppose, because they were women, right? I suppose if there were two blokes, they would have, you know, like Crick and Watson, they would have got a lot more credit, right? So what happened was, these two ladies, Robin Owens, who's in Western Australia, and Maria Conchetta Morone, who was in Western Australia at the time, made the following observation. Suppose we were to take the naughty step, right, and we were to do a Fourier series decomposition. Then what you find is that at that point, and at that point only, you find that all of these are absolutely in phase. And anywhere else, for example here, they're all out of phase. If we go to any other thing here, like a ridge, you find out that they're all absolutely in phase there, and they're all out of phase there. Okay? Now, when I've been talking about local phase, please understand that any single scale phase is completely meaningless. It's the fact that they are coherent or conjugate over multiple scales. That's what defines. So now, we now have a definition of a feature. It's any point in an image where the local phases are maximally, congruently in phase. We now have a definition, not just for steps, for any feature in the planet. Okay? Brilliant, brilliant idea. Now the question is, how do you implement it? And this is a guy by the name of Peter Covesi. He also lives in Western Australia. He was supervised by and married to Robin Owens. I have to tell you that there is two roles that I personally would have found quite difficult. Not Robin Owens, she's lovely. But being supervised by my wife would have been quite hard for me. It would have been bloody hard for her as well. Anyway, Covesi's idea was quite straightforward. You said that as well, did you? Oh, I thought Julia would. So basically, you can think of each one of these at different spatial scales are phasors, so you can just join them up like arrows, and this will be the sum of them. And that's the maximum attainable value if they all had the same phase. If they all had some particular angle, phi 1 was equal to phi 2, phi n, they all line up. And so the ratio of the red one, which is the vector sum of these phasors, to the green one, is a measure of how congruent these things are, right? That's quite straightforward. And that's a very simple equation to write that down. And that's Peter Covesi. You can go check out, this is freeware that's available from the University of Western Australia website, okay? And it works pretty well. There's only two problems with it, and two very fundamental problems. The one is the Hilbert transform, and therefore Covesi's implementation, is only defined for 1D signals. That's a real restriction mathematically. And the second is, you have to add these phasors, in this particular case, amplitude-weighted phasors, and how the hell do you do that and avoid phase wraparound? One of the real problems that we have all the time when you're playing with angles, phases, is how do you avoid phase wraparound? We'll come back and we'll address both of those problems. The first of those problems was solved for the first time, there's been a lot of work since, by Gerald Sommer and Michael Felsberg about 12 years ago, and it's called a monogenic signal. It's only one, there's been half a dozen elaborations since. I'm not going to go on about it because it's a short lecture. So you start out with an image, you take a bandpass filter, like I told you, this is some even bandpass filter, B. You then take your bandpass filtered image and you apply two other filters to it. You convolve with two things which themselves are quadrature pairs. I'll show you what they are in a second. And then from those, the key point is, from those three things that you've just computed, you can find down the local amplitude and energy, the local orientation, so depending on which way your edge is pointing, and your local phase in the image. Now, I'll show you the convolution kernels H1 and H2 in a second, right? And then I haven't shown you here how you combine these over scales. But please understand that you can compute that convolution very fast, and you can pre-compute, this is just H1 convolved with B convolved with I, which is the same as H1 convolved with B. So you can pre-compute H1 convolved with P and H2 convolved with B, and you can compute B. This goes like, you know, this is bloody fast, actually. This is really, really fast to compute. So there's no excuse for not doing it. Okay? So what do these things look like? Well, there's the monogenic triple of filters. You choose a bandpass. I tend to use this one, largely because I invented it with Matt Meller, but there are various others. There's, for example, you could try Gaussians, you can try Gabor, you can try log Gabor, which is what Peter Cavesi does, etc. This one is particularly good because we showed that for texture, there was a PAMI paper that shows for texture that localizes the energy. That's by the by. In any case, there's the bandpass, the even one. You can see it's nice and surrounding. It's rotationally symmetric. And here, in the, as it were, the Y and the X direction are the two other filters that we need. Those are called Riesz filters because the extension of the Hilbert transform to 2D, 3D, 4D, or 157D is due to, was due to the ideas of Riesz. And so there are the two Riesz filters, and you can just look at what they look like. So what's wrong with that? Well, let's now take our image that I showed you to start with, and here I've used the Meller-Brady bandpass. Here's the local energy. I already pointed out to you that as you go up in here, the contrast gets greater. You miss these little holes in the middle. The edges fall off, the ends fall off here. You get this double response. Look at what you get here, though, with the local phase. First of all, it's contrast invariant. You complete all of those circles there. You complete that end, and you get this individual thin line corresponds across that. Contrast independent. Every single kind of feature. All right? It's got to be right. And just to remind you, that's why we got these bright field confocal microscopy images and produced them. And then in essence, what happened was that Bobby Ali, Mark Gooding, Tunda Kalyagi, and myself showed how we could actually superimpose those on a fluorescence image. In this particular case, an HSM image, which meant we were looking for hypoxia staining within these cells, which was the original game we were given. And look how thin that gap between there is. Okay? That's quite a difficult segmentation task. Okay? So that's looking at cells, and this is looking at a couple of the images where here, we're going to come back to this in a minute, non-alcoholic steatohepatitis. This is turning out to be probably the greatest pandemic that faces the Western world at the moment. I'll come back to that a little later. All right, here is some images of the heart using the difference of Gaussians, the dog, which is, if ever there was a filter that was appropriately named, the dog is one of them. So here at multiple scales, we've taken these phase estimated using the monogenic signal I just showed you, and I forget about that. And so here is taking intensity-based image fusion from basically an MRI and an ultrasound, and this is a typical kind of result that we would get using intensities, whereas when we use local phase to do the same thing, this is phase-based image fusion, this is stuff that I do with Matt Meller. We have a lot more places at which we can constrain that registration of these images. Now, why does that work? Well, if you look at the, for example, a pre-treatment image here and a post-treatment image here, you can see first and foremost these are contrast difference. There's a very large bias, which is a B1 in homogeneity, which you typically get down here because the guy's butt is sitting on top of the RF coil. Just to orient you, that's the bladder. These are the hip bones. This is the coccyx. And that's your butt. Well, not yours, but you understand what I mean. The bladder you can see is filled to different extents. If, on the other hand, you take these phase images, you can see that how they've been normalized. It's just a hell of a lot easier to register those two images together, and that's the warped post-treatment image with the appropriate deformation grid. We did this. This is only 9 years ago. Whoops, sorry. And the key point here, and I'm going to come back to it, is that if you take the intensity PDF before and after treatment, you see they're very, very different PDFs. But in essence, if you're trying to do any form of non-rigid registration based on something like mutual information, that's essentially what you're being asked to work from. On the other hand, if you take the phase PDFs, then in essence they're much more lined up, they're much more consistent. All right? And then last year, Julia and I co-supervised, it was a labor of love, but never mind, a particular student, and what we were trying to do was resample MR images. These MR images had essentially what were known as Manhattan voxels in the axial plane. They were very well sampled, but they had very, very long, very thick slices. We had 3 such of those, and we wanted to resegment those images, but this was typical of the axial view, very good, the sagittal and coronal, pretty bad, and here you can see that blocky Manhattan style thing. So what we did was we took, I've only showed you 2 of them here because I ran out of room on the slide, but you take the axial, you take the coronal, we compute the Reese components, and then we essentially have a bunch of rules which are very blocky on the original, but actually by the time you put these things together, you get almost perfect homogeneous isotropic voxels for the image. Now that was one thing, and the second question I asked you was, how the hell do you combine local phases anyway, because you get this problem of phase wraparound? Well, the big problem for phase wraparound, if you don't know it, is you get pi plus alpha and pi minus beta as maybe 2 different phases. You add them together and that's the same as alpha minus beta because they've wrapped around at 2 pi. And this impacts on every single method that uses phases, in particular Kvasis for weighted sums of phases, amplitude weighted, Reese weighted, what have you. And so the problem is the following. Suppose you've got a vector which has got a certain amplitude and a certain phase, theta A, and here you've got B has got a certain phase, theta B. What we really want to do is to take theta A plus theta B over 2. That's the value we want to compute from A and B. So the question is there an intelligent way to address this problem? And the answer is yes, there is. And it's only been known for 130 years. So it may not have come around yet. In the 19th century, mathematics took a wrong turn in linear algebra. It started playing around with rotation matrices. It was a very, very bad idea. It should have gone with Hamilton's idea of using quaternions, and quaternions, which were used in Cayley algebra, eventually became what is now known as geometric algebra. It's a vastly, vastly more powerful way to treat rotations than ever rotation matrices are, even with the Rodriguez ideas. So the question is, can you do that? And the answer is yes, geometric algebra. And how does that work? Well, it works very, very straightforwardly. You work from a basis, so for example, E1, E2, E3 are, for example, the 3 basis vectors in 3 space, and from them you develop what are known as multivectors, E1, 3, E2, 3, E1, 2, 3. And E21 is minus E1, 2, which you may recall if you've ever seen the quaternions. So for 2 vectors of grade 1, it turns out that the multivector is simply the scalar product plus the vector product. So you just get that. And if you look at that, my God, this geometric product has got theta A plus theta B. And what we really wanted was theta A plus theta B over 2. So we're almost there. Well, actually, we can do a little bit better than that because we can remember, since we were told when we were about 14 about de Moivre's theorem, that cos theta plus j sine theta is cos n theta plus j sine n theta to the 1 over n. And so if we just take the square root of that, we can get theta A plus theta B over 2. Okay? So a geometric product and a square root, bingo, we've got what we want. Well, actually, you can do that for any number of monogenic signals, any number of phasors. For example, at any given point in an image, you can take those phasors at different scales, m1 through mn, say, and what you can do is you can simply write down the product and then essentially take the nth root. Wow, oh God, nth root, that sounds bloody hard to me. Well, no, not at all. It turns out you don't need to do normalization, right? There's no need to have the same amplitudes, and in fact they very rarely do. And the number of operations you need to implement this is 4 times n minus 1. This is very, very fast. It's amazing that in this thesis that Julia and I supervised, this stuff amounts to 1.5 pages, and it's probably the smartest idea that's in the thesis, but what the hell. So, in short, well, there were not a lot of other ideas. So, there is a formal definition of a feature. It's based on local phases. 2, in particular congruence of local phases. 2, you can implement it very fast. 3, you can deal with phase wraparound in a principled manner using geometric algebra. Very, very simple, right? Well, that was probably worth listening to. Now let me give you a political statement, and let's look at a regular texture. And we really are better together. For those of you who don't realise, the Scots are about to go and decide to vote to run over a cliff. But, sorry, I mean to go independent. So, here's a regular texture. Why am I showing you a regular texture like this? And the answer is, if you look at any given point in this image, if I asked you what is the characteristic direction, there's one in that direction and one in that direction. In short, there are 2 different directions, 2 characteristic orientations, and if you really wanted to do it, you could also say that one and that one. There are multiple orientations at which this texture repeats. Okay? So why is that a big deal? Well, the answer is that monogenic signal that I was just telling you about assumes a single orientation at each image location, and that's because fundamentally, it's fundamentally, as has been shown by a number of people, it's based around the radon transform. Now, suppose you've got those Riesz components that I showed you a little earlier, then you can compute the orientation, but of course that then throws away the individual information from those 2 things together. So suppose we keep those instead. So this is a simple texture, which in fact was a sum of 2 sinusoids. And if you look at those 2 independent things, one of them just shows you that, one of them shows you that. Whereas if you look at the local orientations and local phases, they actually tend to give you one dominant direction, which is what you'd expect. So what we've gone on to was to look at a Riesz weighting rather than an amplitude weighting. It doesn't matter, we're just taking these local phases, we're just doing a different weighting, but now using those Riesz components. And if you do that, here's my breast MRI, that's what you get from Kovac's phase congruency. On the other hand, if you look at what we get a lot of texture information in here. I'm not trying to make sense of it for the moment, I just want to illustrate that this actually gives you something which is significantly different. Now let's try it on this lady. Those of you who know anything about image analysis will know about Lena. She was for those of you who don't know, Lena was a playgirl, pin-up, and they usually only ever show her head for very good reasons. If you ever looked at Playboy or Playgirl, she's older than me. Not a lot of people can say that. She's older than me, this lady. So this is Kovac's energy-weighted phase congruency, and this is our Riesz-weighted. And what we can do is we can take the difference between them, and the important thing to realize here is if you look at the difference between them, all of the big differences, red is high, are precisely in the areas of the texture that we're most interested in. Well, of course, being an elderly gentleman, I'm most interested in the texture of the feather in her hat. You of a younger generation may be interested in other things, but that's not for me to look at. Now, why do we give a monkey about that? Well, let's actually start thinking about a particular horrendous liver disease, which is primary sclerosing cholangitis. And here is the standard scale of 0 through 6, what is known as the Ishak scale, for characterizing the degree of this illness. And so fundamentally what happens is, here you've got very minimal fibrosis. This is the kind of stuff that Tim was talking about this morning. You've got, when he was looking at this afternoon, whenever it was, when he was looking at the, basically computing the ultrasound and generating strain tensors. So you start off with no fibrosis, and if you don't drink, and in fact if you live a completely and utterly boring life, that's what your liver will look like. right? That's something to feel very good about. You'll still die, by the way, but as you begin to insult your liver, basically you'll get small amounts of fibrous expansion, and they'll get bigger and bigger. Now, actually at that point, if you quit drinking and you quit eating Big Macs and you take regular exercise, you will regain that situation. That's mild disease. Otherwise, you move into this situation where basically those fibrous extensions are beginning to join together. You get this PP portal bridging, and that is now beginning to cut off the blood supply to these little parts of the fibrous parts in here. That's severe disease. There are some quite powerful drugs being tested now that try to get you from here back to here. But actually none of them yet have been proven. And by the time you get around to here, where you've got whole islands that have been isolated, they're cut off from food, they'll die, you're into either hepatocellular carcinoma or cirrhosis. You are, to a first approximation and rounding down, buggered, right? Nothing much you can do about it. So here is a healthy liver, and here is a severe disease. And you don't need much to see that there are significant differences in texture between them, right? The question is, can we use some of the things that we've been doing, which in fact this is what drove what I've just been showing you. And here you can begin to see grade 2, 3, and 4 of features. I'm just showing you them as images, but of course these have all got numbers associated with them. And in essence, what you can see, surely, unless you're feeling particularly ungenerous, is a gradual increase in the density of this stuff. So it should not be hard, right, to put down any texture measure you like, for example, fractal dimension, which is essentially using an application of Richard's law to try to figure out that that is greater than that, and perhaps to stage these livers. And so that's what we've been doing. We started moving towards these Ishak scoring, were healthy, and here's that severe grade. Here's the local phases, and then from that we computed a feature asymmetry. And what did we get out of that? By producing that, we're now correlation with pathology. We get extremely good correlation for 0 and 1. This is the mild disease, mild to moderately severe, and here's the really severe up here. Now, we've only done 150 cases to date. We're currently doing it, we're now currently engaged in a project which will generate us another 250 from Edinburgh and Birmingham, which are full of unreconstructed boozers, and moving then also to doing a similar thing in San Antonio in Texas and in Emory in Georgia. So we will have something in the order of, in a couple of years' time, we'll have 600, 700 people like this. Now, all of that stuff assumes that we can deal with uncertainty. And I just want to run through very, very quickly one point on this, which is everybody asked to deal with uncertainty writes down histograms, and here's an image, and there's the histogram, the number of times versus the intensity of that. Actually, you don't have to do a histogram, of course. You could do a kernel. You could do a straightforward kernel estimator, and you would get the one on the top right, or you could do a kernel estimator with optimal bandwidth, which has got to get you down here. The problem is that computing the optimal bandwidth takes quite a while, but at least gives you the bandwidth. So kind of what we need is something that gives you very accurate estimates of the underlying probability density function, but to be very, very fast, right? So here what we get is the histogram is very computationally efficient, but gives you a very poor estimate. Here is Brady's law, right? If you compute bullshit in a picosecond, the result is still bullshit, all right? So histograms are not good. Can we do better? Well, what's the root of the problem? Here are two images which, to my untutored eye, appear to be different. Now, you may disagree, but I think those images look different. They have completely identical histograms. Why? Because that is just a random re-scrambling of all the intensities in that. Exactly the same intensity in those images, right? So what's wrong? Well, the histograms, all of histograms were based on the idea of population statistics. But actually, images and signals are not populations. Order matters, right? Order matters. If you took a tune and you just scramble the notes and then played it, you get a totally different tune, right? Order matters, yeah? And of course, order matters when we come on to looking at Shannon sampling. If you take order into account, which is what I'm going to show you in a second, that's the histogram of that one, and that's the histogram of that one. So we really do need to take order into account. So how can we do that? Well, one idea that we had, there's been another idea since, but the one idea we had takes a discrete time signal, it takes an interpolation model, and comes out of it with an estimation of the underlying PDF, the probability density function. Okay, so what we did was, if we knew at this particular point the value was b, and this particular point it was a plus b, we could interpolate, and you can write down, just using the inverse Jacobian, a portion of the signal. All right, that's just one. There are many other things, and you can do this in 3D, and we've published some of the most boring papers ever written on this stuff. And believe me, there are some pretty boring papers around, and this one bears comparison with any. So, in essence, what you can do is you can take this image and we can compute this PDF from that image in 30 milliseconds. Just by going back to Shannon instead of actually going to histograms. Going back and asking what is the order, what is the band-limited order in a signal. And I'm going to show you, the reason I want to show you that is one thing in a minute. So here's some stuff that Niranjan Joshi and I did in colorectal cancer, where we were trying to find the mesorectum in order to find the mesorectal resection margin, which I referred to the other day. Whoops, I hit the wrong thing. And this was just doing texture. This is classification. And this is the slide I wanted to show you. Here's a piece of an image, and here is computing entropy using our order method on a 3x3 window and a 5x5 window. If you do it using histograms, you get that. If you're going to use something like entropy as part of mutual information, right, then most people will be doing that. It's not surprising it has a bloody hard time, right? Here, it's going to be a lot better. It's clearly going to be a lot better. It's a much, much clearer signal. The signal-to-noise ratio has increased because you know what the order of the signal is. Right. My last thing I wanted to tell you about, I was so inspired by those talks by Guido and by Xavier the other day, I hesitated to include this, but I just wanted to show you something that it really is of importance to us. Here, in over a period of 8 years, is the same lady's breast. Here, there really was a tumor here, in retrospect, but you'd never have seen it. You never ever would have seen it. This is what is known as an interval cancer. By the time we get to 2000, it's evident, absolutely evident there's a tumor there. And, you know, you could go back and you could try to find it there. So what we're really interested in is looking at the evolution of those shapes over time. And in particular, these shapes that have got these processes which are collagen all around it, and where the density of the tissue is increasing around as the tumor defends itself against the surround. So the question is, can we characterize those shapes which correspond to malignant tumors as opposed to being, for example, completely benign fibroadenomas or cysts? So our task here is one of shape matching, but what we're really interested in is finding significant differences. And if you remember, that's exactly one of the issues that Guido talked to you about the other day in his 2 lectures. It was exactly that issue. And one of the things that Guido talked to you about was, in fact, that the boundary and the interior contain complementary information. So could we combine both of that information together? So we want to have an estimate of the boundary which is robust to noise, and those are pretty damn noisy images, I think, shapes, I think you'll agree, right? And where you can get errors in segmentation. And on the other hand, and which are invariant to articulations because they can be occluded. And then second of all, can we figure out something along the lines of geodesics between points And what we do is, in fact, we use the fast marching algorithm to combine those two things together. So just to give you an idea, here's a couple of dudes from Kimmy's database, which Guido talked to you about. And the idea is that what we're going to do is we're going to produce matches where that entire leg here matches at this truncated leg down here, but the rest of it is matched up appropriately. And here are a pair of craniocaudal and mediolateral oblique density maps from the breast imaging stuff I showed you on Monday. And in essence, this is the matching of the contours around here as we go around with them. So the first thing to realize is that because we want robustness to articulation differences, that rules out projective and algebraic invariance. Okay? So that narrows our choice enormously. So Guido was kind enough to mention some work I did about 20 odd years ago, which were differential invariants. So here you take a shape and you write down its 4 peaks of curvature, and that's all hunky-dory, and the differential invariant is curvature. It's the only differential invariant. But what happens if you put a little bit of noise on this? And the answer is it goes to hell in a handbasket, and that's because it's a second derivative. Okay? The second derivatives will excite that noise. Okay, so differential invariants always are prone, because they're based on second plus order derivatives, they're very prone to noise. Fortunately, there's an alternative, and they're called integral invariants. So here, for example, is that same rectangle, that same noisy rectangle. There's the integral invariance for that, and there's the integral invariance for that, and they're pretty damn close. And that's not surprising, because integral says you're going to add them up, right? You're going to smooth out the differences. So they're not going to be as prone to noise. So what is an integral invariant? Well, there are at least 4 different kinds. And one of them, essentially, is very much like stuff I did with Steve Smith at the years ago, which essentially you can take a circle of a particular radius as you run around a boundary, and that radius defines the scale, and you can look at effectively the integral with basically the characteristic function, and essentially you can run around it and you get an integral measure, integral invariant like that. And you can do that at various spatial scales. Faraz Janan has just been given his thesis for this. So what we end up with is you can then do those, variation of the integral invariant as you run around these shapes, and then the fast marching algorithm will in fact put those on. There's that leg that's being matched to a stump of a leg down here. Well, that's okay, and so here's some of Kimmy's database of shapes. A bunch of fishes up there. I've eaten more bloody fish in the last week than I care to think about. And here are a bunch of mammals, and the same thing down here, and I could show you the numbers, but who can see numbers at this time of the day? So the great news is fish don't resemble mammals. You'll notice, however, I did not put a seahorse in, and I didn't put a whale in. But on the good news is that fish don't resemble mammals. And what about that stuff about the interior? Well, encoding the shape interior can depend on the geodesic distance, and this is quite similar to something that Guido talked to you about on Wednesday, right? It tells you how far apart 2 points in a shape are, in particular how far apart they are on the boundary of the shape. So instead of using the Euclidean distance, you can use geodesic distances, and you can compute that from them. It turns out that the fast marching algorithm is computing the geodesic distances. I don't think that they realized that when they were doing it, but that's exactly what it was doing. And so here are a series of paths from a point here to all kinds of points around the boundary of that shape. And you can just measure how far apart those things are. So to do that, what you can do is what is known as the eccentricity transform. The eccentricity transform is simply taking the solution to what is known as the iconal equation, which effectively is just given by that. It doesn't matter what it is. The only point is that you can prove very, very straightforwardly that the fast marching algorithm computes solutions to the iconal equation. It's a standard differential equation. And that's what the fast matching algorithm computes. And here you can see the evolution of it over time. What do we do with that? Well, here are temporal pairs of mammograms taken several years apart, and then in essence these are taken from the Elizabeth Wendy Clinic in New York. We have 100 pairs of these, and you can look at the evolution of shapes by matching them. And in particular, what we can do for a pair here from craniocaudal mammograms, we can pull out new growth. And that's the thing that we're really interested in. So we're automatically pulling out regions of new growth on the boundaries of these shapes. And let me just skip over this next one to say we can also do the same thing to do false positive reduction. So we can end up by doing a segmentation. We can look at this over multiple scales and basically pull out, we can get rid of something of the order of 90% of false positives. So the very simple conclusion I wanted to come to from this stuff is that actually down here isn't just, you know, the murmurings of some unemployed mathematician and physicist. Actually, there's lots of fun stuff you can do down here as well, right? And that's the real message I wanted to give you today. But since this is the last lecture of this summer school, please allow me just a postscript. The other day, I talked to you about breast cancer, and I talked to you about mammography, and in particular, I showed you some stuff at estimating breast density and a whole series of analytics, and I told you about how you could find out automatically that one person, one radiographer, was compressing the breast less tightly than others. I also told you how you could, on the basis of the mathematical models, figure out automatically the dose. And that's a company that I started together with Ralph Hynam called Martakina, which is in New Zealand. Martakina is one of 5 companies that I have started and which are running at the moment. Here's a second one. Once upon a time, there was a company called Mirada Solutions. Mirada Solutions was eaten by a company called CTI, which was a NASDAQ company, which was eaten by a little German company called Siemens. And then in 2008, we did a management buyout to take back a piece of that technology. And what we were doing was taking CT and PET and doing PET-CT alignment. And this stuff is installed now in over 2,000 hospitals around the world. And in particular, recently, what we've been doing is we've been taking, for example, PET, CT, and MRI, and the kind of applications we're interested in is taking 7 time points where you mark any particular, or you can do it automatically, you pull out any particular area of interest, and you can figure out over time what the volume of tumor is. In particular, you can figure out what its persist and resist measurement is over time. And more recently, we've been doing stuff on dose deformation and adaptive replanning of radiotherapy, and that's what Mirada Medical does. And in another company that I'm involved in that we started 2 years ago, we've been looking at this looming pandemic of obesity. I don't want to particularly, there's none of you who looked particularly obese to me. I think he could do with losing a little bit of weight. He's probably drinking too much of this kind of crap. 36% of the US population is grossly obese. 24% of the UK population are. We have had women show up at the cancer centre for a mammogram whose body mass index is 60. This is not small, right? Yeah. In 2008, 170 million of the world's kids were obese, and 20% of the UK, of the European Union's kids are already seriously obese. We recently had a kid who showed up for a MRI in our centre, and he weighed 65 kilos. He was 10. This is a serious, serious problem. And there are 2 of the reasons why. One in Asia is the very huge, and in the United States is the huge amount of hepatitis C, plus some of the world's favorite foods and some of the world's favorite drinks. We have a serious, serious problem about the metabolic syndrome, which doesn't only cause diabetes and diabetic retinopathies, but also computes as one of the consequences of the metabolic syndrome is either cirrhosis or hepatocellular carcinoma. Huge, huge surge. And down here is showing you the numbers of people, the growth between 2000, which was 155 million people, and 357 million by 2030. And in particular, notice in the so-called BRIC countries, Brazil and India and Russia and China, the massive amount of this. So this is, as I say, the metabolic syndrome. There's a particular surge in, this is not alcohol related, this is junk food and Hep C, right? So this is fatty liver disease and NASH, non-alcoholic steatohepatitis. 30% of the Western population has got liver disease already. Dame Sally Davis, who's the head of the UK National Health Service research, has set this liver disease as the main priority because of the huge surge in obesity in the UK. It will be the leading cause of liver transplant by 2020, and there's a desperate need for imaging biomarkers for drug trials. So what happens at the moment is the following. If you are suspected of liver disease, then you have basically a biopsy. A biopsy takes a 20-centimeter needle and sticks it into the side of you and samples 0.02% of your liver. And from that, you're supposed to have a definitive diagnosis. Okay? It's painful. It costs at least $1,000, and it rises to $4K in complications, which is once every 40 times. It has a 1.1 to 2% risk of significant bleeding and a 0.1% risk of death. And as I said, it samples 0.02% of the 2.5 kilogram liver. This morning, Tim showed you the elastography for a French company. What he didn't point out to you was that actually has severe problems if you've got a huge amount of fat surrounding the liver, because you get an impedance boundary from the fat to the liver itself. So actually, the problem is that a lot of the people we're interested in here have got very substantial amounts of fat. So it's a real problem. Okay, so here are normal and post-pancreatic patients. Okay, in liver, the T1 relaxation time is normally around 810, and here both these patients appear to have a normal liver T1, but this one has got a presumed normal pancreas. That's here. The one on the right is being investigated in here for a significant, what is known as a gallstone pancreatitis. And of course, pancreatic cancer has once it occurs, has a 5-year survival rate of 2%. Okay? So basically, you look at these images, and what we realized was we really do need physics-based fusion between a T1 image, a T2 star image, and a Dixon image, where Dixon is one of the techniques, the 4-point Dixon, as a way of estimating fat. Why do we need image fusion? Here is a standard T1 image that's been color-coded and which appears to be reassuringly normal of a patient. The problem is, I couldn't resist this from something that Tim said this morning. This is the T2 star, which shows massive iron content, which is in fact, if you've drunk a hell of a lot of red wine this week, that is what your liver will look like. Because you'll have massive iron content that you've taken on because of red wine. So, those two things, it turns out that the T1 value is confounded by that, so you have to correct it. You have to correct it based on the T2 star, and you can write down the physics for doing it. And if you do, it turns out that when you've done that, when you correct this image to take into account that, it turns out that the corrected T1 is 959 milliseconds, which is indicative of severe liver disease, which is confirmed on biopsy. So, as I said before, we're really interested in getting this Ishak scores, and we've begun to do a series of clinical trials which we've been publishing in the Journal of Hepatology on trying to, this is the result on 80 patients. As I said, we've now got 150, and that will be 652 years from now. But fundamentally, we have a company now that's trying to do quantitative MR analysis of the liver in anticipation of this pandemic. A last but one example, with my very good friend Nico Karsemeyer, is trying to look at CAD on the breast. CAD on the breast has been artificially supported in the United States by reimbursement, which in fact has had the consequence of killing all development. And what Nico's done is come up with a really, really clever idea of estimating probabilities on a multi-view, for example here from 2004, from both the medial lateral oblique and the craniocaudal view, and here 2006, and looking at the evolution of tumours, and in particular looking at a pair of images such as this, again medial lateral oblique, the craniocaudal, and the doctor will look at these and will not be distracted by having all kinds of CAD marks written all over the bloody thing. Will actually say, I'm a little concerned about that. And only then does it pop up and say, we believe there's a 65% chance of a cancer, and in the corresponding place on the craniocaudal there's an 80% chance of a cancer. That's probably enough to trigger a biopsy. My last example of a company I'm involved in is the following. We're interested in detecting strabismus, or sometimes known as squint. Basically, this affects 4% of kids throughout the world. And if you can detect squint by the time a kid is 7, you can fix it. If it gets beyond about 7, you lose that plasticity, and actually it begins to very seriously impact upon reading and so forth. So the question is, can we develop a system that does that? And what we've got is we've got a phone, we've got a camera with a phone built into it. It's got a little thing in here to try to attract the kid. It flashes with all kinds of funny little lights. You then take an images here, and effectively we can measure the vergence of the eyes, and we can do so very accurately indeed. We write the results out in the form of a report, and that's written out onto an iPad and at the same time uploaded into the cloud. Okay? So what we're doing now is, from all of the devices that we're out, and this is now selling like hotcakes in the States, we're downloading these things into the cloud so that we can build a whole series of statistics about an individual patient, about patients in a particular area, and so on and so forth. So these are just these are 5 companies that I'm personally very heavily involved in. Okay? Now, why did I show you that? Well, to date in this summer school, we've talked about a two-way flow. The two-way flow has been between researchers like yourselves and clinical collaborators. Okay, so these guys, as I explained to you on Monday, are the custodians of the problem, and they do the evaluation. We produce people. It's often forgotten. Our primary product in a university is people. That's what we produce. Okay? So we produce people, we produce ideas, and we produce IP. But there's a third outfit that has to be involved in that, and that's industry, because it's companies, not universities, that sell systems. It's companies that get regulatory approval to use this stuff. Hospitals will buy stuff from companies, they won't buy it from universities. Okay? They need people, they need ideas, they need customers. Okay? So for the last many years, we've worked in three-way collaborations between researchers, clinical collaborators, and industry. Now, my final slide then is, I think we have a key role to play in this process, because we understand the applications, we understand the science-based applied work, and we're actually ready collaborators, which is what Nasir was just telling you about just a few minutes ago. So what for me are fundamentally the take-home messages that you should walk away from here in this beautiful Favignana. What should you walk away with? I would try to suggest the following. There is lots and lots and lots of wonderful science that you can work on. There are many, many clinical problems that need addressing. Huge, huge number. We've barely scratched the surface. There is too much about disease that we have not yet understood, which is what I was showing you about those cellular pathway models the other day. And which is what Doran and I have both gone on about. There can be a symbiotic relationship between academia and industry. They are not antagonistic, right? But progress to do this, to work on these clinical problems, to do work on these diseases, to build these symbiotic relationships, demands the commitment of brilliant young scientists. And that's you lot. The future is not geriatrics like me. The future is you. So get out of here and bloody well do it. Thank you.